Welcome back to another episode of the Rollup and Modular March, Modular April, but we're keeping it going. Today we have the pleasure of speaking with John Adler from Celestia, a really core piece of Ethereum scaling, one of the original believers of the rollup-centric roadmap, and of course, Rob. Welcome in, John. It's great to have you in, and excited to chat about the recent developments.
Glad to be here. Thanks for having me.
Well, let's start by unpacking Celestia. Celestia has a architecture of various types of nodes, all performing their own function. You could even call these nodes specialized or modular in their own right. And they band together to form the framework for modular blockchains, making it very easy for developers to deploy their own modular blockchains. Each of these nodes have a very specific use case, function in the Celestia network. So John, could you start off by telling us about the nodes in the Celestia network?
Yeah, so I actually tweeted recently about this, but there's several different types of nodes. So if you hear someone on Twitter say, "Oh, Celestia nodes need to do a certain amount of work or whatever," then that should automatically be a red flag, because there's no such thing as a Celestia node that does a specific thing. Likewise, there's no such thing as an Ethereum node that does a specific thing. Rather, there's different types of nodes, and each type of node has different properties, security properties, and also different things that it will do. This applies for every blockchain, from Bitcoin to Celestia to Ethereum to Solana. Well, I don't know about the last one, but let's just say at least for Bitcoin and Celestia and Ethereum. So what are some different types of Celestia nodes, and why is it that some of these nodes don't necessarily exist in a normal blockchain, but they do exist on Celestia? And the fact that they can exist on Celestia is one of the reasons that Celestia can have some of the nice properties that it does have. So first is the Celestia full node. So this one here is going to fully download all the block data on Celestia to verify that it is completely correct, and also to verify that it can reconstruct the blocks. This is necessary because even in a blockchain that has data availability sampling, which allows light nodes to determine whether or not a block is being withheld, there's still kind of this corner case where if a block cannot be reconstructed, then like as a whole network, the block is not available. It's kind of a corner case in the data availability sampling protocol, and this exists regardless of the cryptographic specifics of how you implement, or like the underlying cryptographic specifics of your data availability sampling, regardless if you use fraud proofs or KZG proofs or ZK proofs or whatever. There's still this corner case, this edge case, where you may need to reconstruct the block. So full nodes perform that service. They will fully download blocks and attempt to fully reconstruct them. Obviously, they're more expensive to run, so we would expect a fewer number of them. But one thing that's very important is that full nodes aren't required for node runners to contribute security to the network, which we'll talk about in a second. So on the other end of the spectrum of full nodes are light nodes. So these light nodes perform data availability sampling rather than fully downloading blocks. So this means they will check a very small portion of the block, of every block, and importantly, it's not a portion of the block that is proportional to the block size. Rather, it's a fixed number of parts of the block, regardless of how big the block is. The block could be 1 gigabyte big. It doesn't matter. You're still only checking the same number of different parts of the block, and the parts all have the same size. And through this process of data availability sampling, combined with enough light nodes performing this data availability sampling, the network as a whole can determine securely whether or not a block is available or not, without these light nodes having to fully download blocks. So this is kind of an amazing technique that allows Celestia to scale while also allowing users to verify that the Celestia blockchain is correct without having to do a lot of work. Because, like we know, one of the reasons that blockchains have any sort of limit on their throughput is to allow end-user verifiability. Right, if we don't care about end-user verifiability, then just run it in some Web2 AWS database. The whole reason that blockchains are so important, like the one of the very important properties is the ability for end users to verify that the protocol rules are being followed by the block producers. Okay, so now these light nodes don't do reconstruction. I said there's an edge case where, okay, they can perform sampling, but they don't do reconstruction. So who does reconstruction? We could say, well, full nodes do reconstruction of the whole block. That's correct. But can we have reconstruction performed by a node that is not as expensive to run as a full node, a node that does not fully download blocks? And it turns out you can. You can have nodes that don't require fully downloading every single block, and these nodes can still contribute to the security of the network. How does this work? So there's kind of two orthogonal axes that what we call partial nodes, but these could also be called sharded nodes. There's kind of two orthogonal axes on how these partial nodes will split up their responsibilities. One of them is they could download parts of every block. The other one is they could download not every block, but every whatever number of blocks. Let's say one every 1,000 blocks. Then these partial nodes can perform the work of reconstruction, can perform the work of checking that the protocol rules are being followed. And this act of checking that the blocks are correct, the nice thing about Celestia is that this check can be performed statelessly. In other words, it does not require nodes to know what happened in every previous block in order to check that the current block has been constructed correctly. Because the construction, like the reconstruction process that I was talking about, is completely stateless. It happens on a per block basis. It doesn't happen, like it's not something that requires you to know all the previous history to then verify the current block. Since it's stateless, it means that you can actually shard this work, you can distribute it across multiple different nodes and have each of them be responsible for a subset of all the blocks. For instance, if you have a large number of partial nodes, each partial node can, instead of fully downloading every block, they could fully download, let's say, one out of every 1,000 blocks. And in this way, they can perform this reconstruction process if needed on those blocks without having to fully download every block. And since it's a stateless process, it means they're contributing security to the network by there existing some nodes that can verify this edge case, verify that the rules of the protocol are being followed correctly by the block producers. And these partial nodes can be very cheap because they don't need to download every block. They can download one every 1,000 block. So now you can run it on a very cheap computer versus requiring a very expensive computer or a powerful server that would have to download every single block. And again, this is accomplished because building each block is a stateless process. And in a traditional blockchain, such as, let's say, Ethereum, Bitcoin, Solana, the vast majority of the work that's being done in validating the block is not independent of other blocks, but rather it's about processing transactions, where the effect of a transaction depends on all the previous transactions in the blockchain. So you need to know the state of the blockchain. You need to know everyone's balances to check that people have enough balances to know the current. You need to know the current amounts in the pools, if people are doing a swap, et cetera, et cetera. You need to know all that, and to know all that, you need to know everything that happened in the past. Celestia is different is that you can do things on a per block basis. So this is part of kind of what I was trying to elucidate in my short Twitter thread about this topic, is that Celestia partial nodes, which you could also call sharded nodes, allow users to, in the worst case cost that a user needs to pay in order to contribute security to the network is actually very low if they run a partial node. And they don't need to run a full node to contribute security to the network. Full node just do extra work, which is like a nice to have. Kind of like on Ethereum. Ethereum has these archive nodes that serve historical state. And it's very convenient for the network to have archive nodes. But if all of the archive nodes suddenly disappear, the network wouldn't just become insecure. No, because you can reconstruct an archive node from a full node. You just need to do more work. So it's a convenience thing, not a security thing. Similarly, the existence of Celestia full nodes is a convenience thing, that it could be more convenient for someone to connect to a single full node that has all this data versus multiple partial nodes, but it's not necessary for security for users to run a full node to contribute. Like full nodes do not contribute any unique security properties to the network. They're purely a convenience thing. Okay, so I hope that's kind of a summary of a subset of the different Celestia node types. There are several others. There's validator nodes, there's archive nodes, etc. But these kind of form the there's fundamentally, a few different Celestia node types, but these partial nodes or sharded nodes, if we want to call them that, are something that other blockchains that don't operate as a data availability network, ones that aren't stateless in the way that Celestia is, just cannot have. It's just not a thing that's possible in those networks, and it's something unique to Celestia.
So, John, I want to hone in on the word of statelessness, because that's something that I've heard some other protocols use, but I just want to make sure that we're all on the same page when we say statelessness. So the idea that we unbundle historical state and current state means that we can put the historical state in the archive nodes, and we can verify the current state using this sharded node or a light. And I kind of want you to help me here, because we kind of push all the historical state into the archive node, and then it means that these partial nodes are able to operate in this stateless way. And because they're able to do that, they're much lighter, and it means that you can run them with much lower node requirements, such as running them on your own CPU, or rather like low storage or low performance type of GPU or chip. Is that a fair assessment of the difference between these archive nodes that store historical state and then these partial nodes that are verifying the current state?
So the assessment and the conclusion are directionally correct. There's some wording things that aren't exactly precise. So I'm gonna pull on my I'm gonna be really pedantic here and
Please.
and kind of talk about the distinction between block data and state. Lots of people get mixed up between the two because they have a lot of similarities, and in normal blockchains you kind of need to keep both around. But so the difference is that state is whatever is required to verify new blocks. It's something your full node, or your, I guess, partial node, as it were, needs to keep around in order to verify the next block. Block data is things that are only needed for the current block, and then can be dumped into something like spinning a disk, something that's cold storage that isn't accessed very often. It doesn't require random access, basically. So those are kind of the two different things. So in a normal blockchain like Ethereum, for instance, that has smart contracts, that has execution, etc., the state can be quite large. It can be hundreds of gigabytes, because that contains all of the account balances, etc. And blocks are actually quite small. And blocks are largely transaction data that mutate the state. But on a blockchain like Celestia, it's quite different in the sense that what is needed to be kept around in order to validate a new Celestia block, if you're running a full node or a partial node. This is where I kind of skimmed over this detail, but partial nodes don't keep around no state. They keep around the Celestia state, but then they don't need to fully download all the block data. And it turns out, because the Celestia state machine is very minimized, it's very minimal, the state they need to keep around is very, very small. We're talking on the order of like 100 megabytes or something. It's very small. So it's not zero. So if I call like partial nodes stateless, it's an approximation in the sense that compared to Ethereum, they're essentially stateless. Technically, they're not. But the distinction is basically that these partial nodes don't have to do a lot of work. They do very, very minimal work to actually process state changes. But a lot of the work that they're doing, 99%, is going to be processing block data. And for block data, you don't need to keep that around to process the next block and the next block. You only need it to process the one block that you're processing. State needs to be kept around to process all future blocks. So that's kind of the distinction, in the sense that the vast majority of the Celestia block work that's being done is processing block data, not state transitions. The vast majority of work in traditional blockchains is processing state transitions, which have an effect on the state, and all of that needs to be kept around. You can't put that into cold storage, and very little is about processing the actual block data. Does that answer your question?
It does. I got one follow-up question, and I'm sure Andy's got questions as well. My follow-up question is this idea of reconstruction. I want to try to unpack the difference between reconstruction and verification. So let's say I know the state at T2. Do I also need to know the state at T0 and T1 to make block at T3? Or can I just use T2 and then reconstruct and then verify the block that comes next at T3?
So this is where the distinction between the state and the block data comes in. So you don't need historical state. So you don't need to know what the old state was. You only need the latest state. And in general, in any blockchain, you only need the latest state. But the question is also around the block data. Do you need any block data? And the answer is you don't need any block data on any blockchain, Celestia or not, to process subsequent blocks. You only need the state. So in Celestia, the state is almost non-existent. So essentially, it's stateless to process new blocks compared to traditional blockchains. While in a traditional blockchain, since 99% of the work has to do with state, then you need to keep all the state around to process new blocks. Does that answer your question?
Yeah. So in a traditional blockchain, you would need to know the previous blocks in order to construct the new block, but not
right.
Not in
so
Celestia.
You need to have processed the previous blocks to get the latest state. Like you would need to process the previous blocks. You would need to process all of their state transitions to get the latest state. While in Celestia, since the majority of the work is block data, you would not need to process the previous block's block data to verify the current block's block data. And that's the important distinction. That's why it's so powerful to have a blockchain that's nearly stateless, that the 99% of the work is block data, because that can be sharded. You can shard that responsibility. Since a node does not need to download every single block to process new blocks, they only need to download the block as it comes in, whichever one they're assigned to, or whichever one they want to verify, which could be a very small fraction of the total number of blocks.
And that means that you can verify you can download one of the blocks. I can download a different block, and because I don't need to have downloaded all of the blocks, I can just download mine. You can just download yours, and then we can reconstruct the newest block together.
Yes.
Cool.
You can reconstruct it together, and you can also reconstruct it independently.
Okay.
I think the big distinction is there's no smart contracts on Celestia. The only thing that is that only smart contract execution is staking, I think, and sending transactions.
Much, yeah.
Right.
There's
and so
staking and transfers. There's a few other very, very minor things, but basically, yeah.
There's no Uniswap on Celestia, right? There's just no capability for that, and it was purpose built for that. So
exactly.
We can then create this idea of okay, this blockchain. I mean, that's where the whole modular thing comes in. But to kind of rewind, so we've got full nodes, which are the highest cost of coordination for reconstruction or a reorg, which is effectively a catastrophic event. And you've got light nodes, which are able to facilitate data availability sampling, which is almost like the magic sauce of Celestia. Is this idea of DAS by light nodes, and then you've got these partial nodes, which we recently had a live stream with the founder of EigenLayer, and we talked a lot about the cost of coordination and how having to go back and download the entire full state of a blockchain is quite hefty. And the ETH Classic fork was just this big example of how much that cost the Ethereum network. But we've got these partial nodes where we don't have to go and rely on the full nodes to kind of give us that state back. We still have this kind of lightweight version. And you keep bringing up Bitcoin, Ethereum, and Solana, and something tells me that you've seen this chart that was circulating Twitter this weekend, which is a chart with a y-axis here of small blocks and large blocks, and non-VM and VM. And we've got Bitcoin in non-VM and small blocks. We've got Celestia in large blocks and non-VM, and then Ethereum in VM, small blocks, and Solana in VM, big blocks. And you've been kind of touching all on this, and honestly, I just wanted to understand what you think about this kind of framing.
I actually hadn't seen the diagram, or the chart,
Okay.
whatever you want to call it that, but I can imagine it in my head.
Here you go, sir.
I guess it's a decent framing. Yeah, I can see that. I guess it's a decent framing. I'm not sure how useful it is, in the sense that, like, it's true, but also how useful is it to, like, can Bitcoin act as a modular data layer just because it's a non-VM? The answer is
Yeah.
not really. Also, Bitcoin does have a VM. Just because Bitcoin doesn't have like a Turing complete VM doesn't mean they
Like
don't have
smart
any
contracts.
VM. They do have smart contracts there with Bitcoin script.
Yeah. But I think this is almost what you were getting at, is like, okay, Celestia has these large blocks, and there's no virtual machine, there's no smart contract logic, there's no execution, or very minimal, perhaps it's stateless. And so it kind of fits in this new quadrant. Like there's not a quadrant here that is kind of part of this in the past. So I'm just going to pull this down, and we can continue the conversation. So we understand the Celestia architecture. We understand the nodes. We understand how data availability sampling works, and also why Celestia has been kind of made for data availability and for data publishing. So now we've got Blobstream coming in, and we've got this idea of data attestations. We've got ZK proofs with succinct. Blobstream has just gone live in testnet for Arbitrum Orbit and Base. What is Blobstream for somebody who has a fundamental understanding of data availability, but not an extremely technical one?
Sure. So Blobstream, to kind of give the TLDR, is a one-way relay. I'm going to avoid using the term bridge, and I'll say why in a second. It's a one-way relay of attestations around the fact that data is available in Celestia to another blockchain. In this case, an EVM, one or more EVM-compatible blockchains, such as Ethereum, Arbitrum, Base, Optimism, whatever else is Ethereum compatible. In the future, I'm sure we can have additional blockchains to implement a Blobstream verifier, such as something in this line of VM. Why not? Or even Bitcoin with BitVM. Why not? There's nothing inherently stopping us from doing that. So it essentially allows all the blockchains to leverage Celestia for data availability. So you can essentially use Celestia in any ecosystem. And how does it work? And how is it different than a bridge, a traditional bridge? So a traditional token bridge is two-way, and it also involves the movement of assets, tokens, which has a few downsides, one of which is that if you manage to move tokens across the bridge without some sort of authorization, it becomes very hard to claw them back as soon as anything happens with those tokens. Right? So as soon as they go into like some sort of DEX, as soon as they go into a mixer, then it's over. You have to do a rollback, right? It's basically it's extremely difficult to kind of roll that back because it involves tokens and is also two-way. Which involves additional communication complexity, etc. Blobstream is different in both of those ways, in the sense that it's unidirectional, it's one way. It's an attestation around the fact that some data is available in Celestia, and this attestation is relayed in one direction from Celestia to another blockchain. Let's say some EVM compatible blockchain, just for the sake of simplicity, because that's there's a verifier contract written for the EVM that exists today, not so much for other environments. What does this give us over other schemes for leveraging off-chain data availability solutions, such as data availability committees? So one of the issues with data availability committees and other protocols, such as restaked data availability solutions, or anything that's entirely on-chain, is how do you do slashing? The one question you should ask whenever someone says, okay, we have some mechanism to increase the data availability throughputs through some off-chain mechanism for your EVM-based chain, you should ask, okay, what are the security guarantees? Well, you have to ask two things. One of them is how much is bonded? So how much can be penalized if these actors misbehave? And the second is how do you penalize them? And you need both. And a lot of people will only talk about the former. They'll say, oh, our protocol has so much money bonded in it. It has, half of Ethereum stakers are bonded in this restaking protocol. And there's so much security. But if you can't penalize against this bond, then it's worthless. The bond means nothing, right? A bond is only as not as important. It's only as useful as how much you can actually penalize against that bond. If you can't penalize against it at all, then it's just a deposit that can be withdrawn. It's just capital inefficiency. So you need to consider both cases. With the data availability committee, there's no bond. It's purely just reputation based. Right? You have 5, 7, whatever actors. They're highly trusted. They're highly well known. If they misbehave, their reputation is in the shitter. Kind of like, let's say Silicon Valley Bank, right? Let's use that one. How about
in the absolute shitter, man? Absolutely.
Well, I mean, the reputation is pretty bad, but has that helped their customers? Not so much, right? They needed some sort of centralized bailout. So reputation it's not exactly worth much, especially once the thing's already collapsing. Then whatever, it's done. The other alternative is you have some sort of on-chain protocol, some sort of committee that's on-chain. It could be however it bond themselves, right? It's something on-chain, and there's ultimately some isomorphism on a DAO. But the problem with this is, how do you slash? How do you actually determine, since everything is purely on-chain, how do you determine that these actors have misbehaved off-chain? Data availability is not a uniquely attributable fault. That's one of the reasons we have to do all this data availability sampling stuff, because you can't prove that data is available to any other node unless the other node unless your proof is just here's the whole data. Like, sure, that could be a proof, but it's not exactly a good way of doing it. So since you can't do that, you can't do anything on chain unless, of course, you just kind of reduce. In the worst case, the on chain system is literally just downloading all the data from off chain, which is not that doesn't work. That just doesn't fly. So how do you slash on chain? You need some sort of other committee, some sort of other way that is not going to be as secure as the bond to enforce the slashing. For instance, you could have some secondary token that could control a DAO, and the DAO could determine through some token-weighted vote to enact the slashing, right? But then again, the security is derived from two components. One is how much is bonded, and two, how do you enforce slashing on that bond? And in this case, well, your security isn't the large bond. Your security is really potentially this much smaller value, a smaller amount of tokens, which could have a fraction of the bond in terms of their dollar value, that are controlling the DAO, and they determine how the slashing gets. How they determine how to slash the bond. That's just one way you could do it, but you could just ask your protocol of choice, how else do you do slashing? Another way, instead of having the DAO do it, they could just have their company do it, or like a multi-sig or whatever. But then you're just back to reputation. Like, reputation is ultimately what is securing this protocol, not the bond. Okay. How does Blobstream differ from this? And one of the nice things is the fact that since there's no tokens, you don't have to worry. Since it's not a token bridge, you don't have to worry about the problems of there's a bug in the bridge, and after that tokens go rampant and stuff. It's purely just passing messages around, and not just around, but in one direction. So how is slashing done in Blobstream? The way it works if there's either a bug in Blobstream, or if whoever is doing the off-chain work, which in this case is the Celestia validator set, misbehaves, they need to get well, if there's a bug, I guess there's not. There could be a penalty, there could not, who knows? But if there's misbehavior, then they're going to get slashed. So who enforces the slashing? This actually required the Celestia validators to misbehave on Celestia itself, not just on the bridge. Because not the bridge, sorry, the relay. It doesn't just require them to misbehave on Blobstream, it requires them to misbehave on Celestia itself. Which means they've now corrupted Celestia itself. And what happens if you do that? Well, you're going to get slashed. So this is going to result in 2/3 of the Celestia validator getting slashed, and this will be enforced through Celestia social consensus. And generally speaking, for any moderately mature blockchain, you should assume that the cost to corrupt social consensus across a large community is effectively infinite. It basically can't happen, right? Like if you ask the Ethereum community, hey, Ethereum, can we, mint 1 million Ether and give it to Robbie, right? The Ethereum community is going to say no, and there's not really any amount of money that you could pay them to do that, right? Because that would kind of erode the amount of money you'd have to pay them, it wouldn't be like 1 million Ether. You'd have to pay out the wazoo. It would be way more than the amount of staked Ether. Way more than that. Because it would basically destroy the entire chain forever if they did this. Similarly, the Bitcoin community or the Celestia community, basically on any blockchain that has established a decentralized community, the cost to corrupt that community in such an obvious way of you have this obvious, very obvious and provable and attributable corruption to the system, and then you just let it happen, the cost to do that should be modeled as infinite. And this is very different than, for instance, one company who will have its reputation tarnished right as they're going bankrupt, so they don't even care, or some DAO where the amount staked on that DAO is a tiny fraction of the bond. So the guarantees around slashing in Celestia with Blobstream are not even close to comparable to the guarantees or lack thereof that you'd get out of any other alternative or off-chain data availability solution for Ethereum and EVM-based chains. So it was kind of long-winded, but did that give an overview of Blobstream and how it's different
I think
than
so
other
for sure.
protocols?
And I brought up the graphic because I think that it will help people understand, and also us. But I think, understanding the differences between off-chain DACs, or effectively just off-chain groups of people saying yes, this is good, and yes or no, this is not. That's kind of that was step one, I think, with Validiums and early stage rollups and things, or early stage scaling designs, and now kind of moving into slashing and having the validator set be the ones which verify the truth, and then them being penalized. So when the validators will be verifying in this attestation. If you look at the graphic, that's kind of the attestation phase, right, where the validators are signing that the data is truthful and available, and then passing it on. That's where the slashing could occur. Is that right?
Slashing doesn't happen in the DA attestation, in the sense that the DA attestation is what is relayed from Celestia to Ethereum. The slashing will take effect in the actual data availability layer itself. So it's the little bubble on the right that's the Celestia. So it would essentially be the social consensus of the Celestia community will determine that there's very easily provably a fault in the Celestia chain, because the validators have to sign over something that is malicious, some invalid Celestia block, essentially, in order to produce an invalid DA attestation. So this is, it's trivially provable because of that. You run a Celestia node. I shouldn't say Celestia node because we know those don't exist. You run a Celestia partial node, and you can verify that the block is invalid. That has been relayed or unavailable. So why can we do this when we couldn't do this? We couldn't have this nice guarantee a couple years ago. So when Blobstream was first introduced as the quantum gravity bridge, there's that word again. We should have called it quantum gravity relay. A couple of years ago, or I think it's been maybe a year ago, maybe 2 years ago. Time flies with COVID. This is the temporal distortion field. Back then, we used kind of a much more naive approach that did not use EK. That essentially it was a situation where validators had two keys. Since Celestia is based on the Cosmos stack, Celestia validators use ED25519 signatures. But in Ethereum, to verify those is very expensive. So the old quantum gravity bridge used a situation. It was a situation where every validator had two keys. One that they would sign on Celestia, another one that they would sign with on Ethereum. And the Ethereum keys would use ECDSA with SecP256K1, similar to Bitcoin, Ethereum, and those kind of chains that use kind of this older signature scheme, which is still fine. It is different, and it's much more expensive to verify an ED25519 signature than an ECDSA signature on Ethereum specifically. And the initial target for quantum gravity bridge and Blobstream would be EVM based execution environments such as Ethereum. So this led to a bunch of complications because now there's two keys. It was a whole bunch of complications. I'm not even going to go into it. But the kind of important takeaway is that you didn't have, in such an easy way, this nice guarantee that to corrupt the DA attestation, you had to corrupt Celestia itself. Now with the new scheme, which internally we call BlobstreamX, developed by Succinct, you do have that guarantee. So how does BlobstreamX work? It essentially runs a protocol where it generates a ZK proof that a Celestia block has consensus over it for all Celestia block headers. And essentially, the ZK proof verifies all the very expensive to verify in the EVM ED25519 signatures. It verifies them inside a ZK proof, and then you only have to verify that one ZK proof for a whole batch of block headers on Ethereum at a time. So this substantially reduces the cost, but also it means validators don't need to have these two different key pairs; they only need one. Then the one is exactly the same key pair that they use to sign Celestia blocks. So in order to corrupt the system with BlobstreamX, they would actually need to sign over an invalid or unavailable Celestia block, which is much easier to prove than if there's an extra key pair involved. And this protocol, the nice thing about BlobstreamX by Succinct is that yes, while it's currently available on EVM-based execution environments because there's an EVM verifier, it's very easy due to the nature of ZK verifiers. A lot of them are written on Rust and stuff. It's very easy to port it to, for example, Solana. If you wanted to run it in the Solana VM, then you could run, you could have Celestia, you can have L3s on Solana with Celestia underneath for data availability if you wanted to have this. So kind of to expand on this a couple more points, I think a couple of weeks ago, Succinct announced, and Celestia Labs also, that Blobstream was deployed on Base, so the Base rollup on Ethereum. So this means you can build L3s like a Base mainnet. So that means you can build L3s on top of Base that leverage Celestia underneath for data availability. Just earlier today being the date of recording, so Tuesday, April 2nd, we announced that Blobstream is going to be coming to Arbitrum. So this will allow you to deploy Arbitrum L3s this is kind of unique thing among all these DA integrations. These like off-chain DA integrations. This is working fraud proofs. So it'll allow you to deploy Arbitrum Orbit L3s on top of Arbitrum Nitro, if I remember correctly, with actual working fraud proofs. So it's currently undergoing audit, but I believe it's going to be on testnet. Either it is now or will be very shortly, and will be in mainnet obviously in the near future. So already now and more so in the near future, you'll be able to leverage Blobstream in production on mainnet to deploy L3s on top of layer 2 rollups on Ethereum for massively increased data availability throughput and also massively reduced costs.
Yeah, and today's announcement was exactly that with the Orbit chains. Arbitrum Nitro has been pushing the fraud proofs, which I think is something that the Ethereum community gets a kind of a lot of a bit of a rap for. Have just a couple minutes left, so we have some like rapid fire questions in a way. Feel free to elaborate as much as you like. I'll go first, and I'm sure Rob's got some as well. My first one is like, does the differentiation of data availability costs really matter that much after a certain level of scale in terms of orders of magnitude cheaper than Ethereum post Cancun? Like, are we going to see differentiation in teams building out or choosing their stack based on these slight differences in costs, or are there other metrics or characteristics that we should be looking out for as far as differentiation amongst these DA layers?
Yeah, so yes and no. As always the case for a lot of these protocol design and protocol choice questions. So no, in the sense that all else being, for certain use cases, the difference between a fraction of a penny and a smaller fraction of a penny is nothing, basically, right? But imagine you have a huge volume, then even small differences can make a substantial difference if the volume is huge. And this is kind of where the crux of the maybe no comes in, which is that all blockchains have some sort of constrained resource, because there's a constraint on how many resources they can provide to the network or to the world, I guess. It's probably good. I don't know how you want to describe it. They have a constraint on how many resources are available. Manifest as some sort of limit on their throughput. This could be in terms of megabytes per second for modular blockchains, which one of my pet peeves is when someone quotes transactions per second for like a data layer, which makes no sense because it's all about bytes per second, or transactions per second or gas per second, whatever. There's going to be some sort of upper limit on these things. They don't provide, it's not unlimited for any blockchain. And that's kind of where the tricky thing is, which is that once this limit is hit, a fee market will emerge unavoidably. Well, it's either a fee market will emerge or a blockchain is going to start just crapping out and just shutting down. So we're gonna assume a blockchain is not going to do that. So a fee market will emerge, where users are going to start bidding against each other for inclusion in this very limited block space. So if you look at two protocols and you say, okay, both of them are super cheap, that basically means nothing, because the only reason they're cheap is because neither of them have hit this situation where a fee market will emerge. And so like, if one blockchain says, they're 100 million times cheaper than the other one, and one of them is a fraction of a penny and the other one's 100 millionth of a fraction of a penny, this comparison is disingenuous because these numbers mean nothing, because it's clearly not in a fee market situation. So what's the important parameter is actually not the cost, it's actually the throughput, because the throughput is how many users will be able to use the blockchain or use this protocol, whatever. We'll be able to use this thing before a fee market emerges, and potentially the costs become prohibitive. So the throughput is the actual important number. And in that context, Celestia has a substantially higher throughput than, for example, post-Cancun Ethereum. Obviously,
And you're speaking
post
about in megabytes per second, not transactions per second, or transactions per second.
Well, that's correct, but also in another way. So not transactions per second, but yes, in terms of megabytes per second, Celestia has greatly increased throughput, which means that if they're both used negligibly, then okay, it doesn't make much difference. But as soon as you start using it more, as soon as you get to a point where rollups explode in usage, which we actually saw happen not too long ago with things like blobscriptions, then you're in a situation where a fee market emerges, and if one protocol can do 1 unit of work, the other per second, the other one can do 10. if you're in a situation where you can do 2 units of work, where the user demand is 2 units of work, the first blockchain that can only do 1 is going to have a fee market, while the second one won't. So it all depends on where you are on this demand curve, but the one with more throughput is basically universally, in all cases, regardless of where the demand is, going to have lower fees. And the throughput of Celestia is much greater than, for instance, post-Encune Ethereum. That's the one thing. But the second thing, and this is also important, is post-Encune Ethereum allows 3 blobs per block as a maximum. Before someone on Twitter says, no, the maximum is actually 6, that's actually wrong. Because the maximum is 3, and double maximum is 6. People always use the framing of, blocks can be half full, and then they can be full. But really what it is, blocks can be full, and they can be twice full. Which if someone complains about what I just said on Twitter, I'm gonna rip you a new one. So please do if you think I'm wrong, because I'm excited to rip you a new one on Twitter. But basically the maximum blobs you can have per block post Encune is 3. And think about how many rollups are in Ethereum today, and think about how many rollups there are going to be, right? We envision a world with 1 billion users, 1 gigabyte blocks, and 1 million rollups. That's not going to fit in 3 blobs per block. So Celestia not only does it have higher throughput, but it also has, just based on some protocol details, it has a much more flexible usage of its block space that allows you to have a much larger number of blobs. Now, I'm not talking like 10. I'm talking like you can have like 500 blobs if you want. They'll obviously be smaller, but you can have a much larger number of blobs. It's much more flexible in that regard. It doesn't have this restriction. So in both of those ways, Celestia will provide much more throughput than currently exists even in post-Encune Ethereum, and much more, for the level of security that it provides than any other off-chain data availability solution for Ethereum.
I think that's a really interesting mental model about the fee markets. The other one that I have is we had a really interesting presentation about monolithic and modular structures converging in a similar path, where monolithic structures scale modularly and modular structures are going to enshrine more. And understanding that Celestia kind of pioneered this modular ecosystem, there's now this move towards enshrining a ZK verifier for kind of further efficiency. One could call this moving from a more modular to a more integrated or monolithic structure. Why exactly is the ZK verifier something that Celestia is looking to move towards? I understand kind of like the bridge situation in terms of L2 to L2 and L2 to L1, and perhaps you could elaborate a bit.
Yeah, so it's basically entirely because of the bridge situation. So
Okay.
it's so I want to say that Celestia isn't stateless. I was using that word more because it's shorter to say, but the correct response of this, or the correct description is the state minimized, in the sense that the state machine is extremely minimal. So sure, it's not stateless, but state minimized. But you could also argue, since it's not completely stateless, it's state minimized, then it's not, it's not some pure ideological, pure version of the lazy ledger white paper, which is true. So it's already one step removed from that. It's already one step towards, you can call it some settlement layer if you want to call it that. I mean, that expression means nothing at this point. But the point of snark accounts, we call them snark accounts, names subject to change. We're trying to find, we're brainstorming some cute names. There are some bad suggestions. There are some good suggestions. Okay, there's some bad suggestions. There's some medium suggestions. I don't think we found a good name, but we'll call them snark accounts, or the ZK accounts. The purpose of them is to allow for secure two-way bridging between Celestia and rollups. In this case, it's bridging, so it's bridging of tokens. Such as TIA, or if you happen to have any other token representations, but let's say mostly TIA, between, to and from Celestia and rollups on Celestia. But the reason that, both the proposal and the reason for the proposal is to enable this bridge without harming substantially the trust minimized nature of the Celestia state machine. But sure, you could say, okay, well, let's go full EVM, let's build a whole Turing complete state machine. Now you can bridge tokens to and from, smart contract bridges. But the issue with that is then it's not state minimized anymore. So snark accounts are this nice compromise where we get trust minimized bridging, with certain constraints. Obviously, you can't have fully expressive message passing. It would be something simpler like a token bridge between Celestia and rollups. And this kind of greatly reduces the friction of running rollups in Celestia and paying fees in TIA, et cetera, et cetera. It reduces a bunch of frictions, both between rollups and between rollups and Celestia. And it does so while not harming the state minimization property as much as possible, right? Because snarks are kind of like a thing where you can express these complex computations with very little complexity on the base layer, because the verifier is much simpler than what's happening inside the actual proofs.
Awesome. All right, one last one. I know that we're super low on time. You guys chose a model for data availability sampling and for data availability that wasn't around KZG commitments. I understand that you guys use erasure coding. However, this kind of KZG polynomial math verified verifiability for my terms isn't what you guys chose. What's the trade-offs? Why is that design choice? Why was that design choice made?
Primarily due to time, in the sense that, there's two reasons. One of them is primarily due to time, in the sense that Celestia is live on mainnet. All the protocols that have attempted to go the KZG route are not. So that tells you everything you need to know with respect to time to market. And like, it's not just that they're not, but they're a couple months behind. As Celestia has been on mainnet for almost 6 months, and nothing else is even close. So that's the first thing. Time to market was substantially faster, and it could be done without any compromises with respect to the cryptographic compromises or whatever, to the fraud proofs or whatever. The bad encoding fraud proofs and stuff are all there. So like data availability sampling has this security that you get if you read the paper with respect to the existence of fraud proofs. It's not like some protocols or fraud proofs don't exist. So it's all there, and shipped clearly substantially faster than KZG commitments. So at the time that this was being developed, KZG commitments were very immature, both in terms of the general knowledge about how they work cryptographically and also the proving costs, et cetera, and also how to verify them on Ethereum, right? Like a lot, if you've talked to any of the ZK rollup teams, they'll tell you that integrating KZG commitments into those ZK rollups, verifying that verification is non-trivial. It's a lot of work, right? While verifying something or integrating something in Blobstream is substantially less work, right? Like it can be done with substantially less work, substantially faster. So that's kind of the first point. The second point is that you don't really get substantial benefits out of KZG commitments. Some people say, oh, you remove a synchrony assumption. You remove the need to wait for some honest party. You don't need an honest party. But that's not really true, because even with KZG commitments, that's only for sampling. Yes, KZG commitments remove the need for bad encoding fraud proof during the sampling process, but they don't remove the need for reconstruction. And like I said, there's two parts to the whole data availability sampling protocol. One of them is sampling, the other one is the reconstruction. And even with KZG commitments, you still need nodes to be able to do that reconstruction, which also requires a synchrony assumption. So you can't remove entirely the need for multiple nodes communicating with each other over a synchronous network, and therefore you can't remove the assumption that there's other honest nodes in the network entirely, because of that second part. And that second part has nothing to do with ZK or not. It just can the nodes in the network talk to each other to reconstruct the block. So because of this thing is you don't get yes, you get some benefits of KZG commitments, sure, but you don't get you don't get a thing where it's just strictly better in every way. Sorry, I guess it is strictly better in every way except for the obviously the cost to develop. But you don't have a situation where it's so much better that it's you have to go straight to that. No, that is not the case. And of course, once KZG commitments are mature, I fully expect the Celestia community to endorse and approve of an upgrade to the Celestia protocol that will allow migration to KZG commitments. And we thought a lot about how we can update the protocol without while also retaining backwards compatibility. In other words, while not harming existing rollups and other protocols that are building on Celestia. So you just upgrade it to use KZG commitments for sampling. So there's always an upgrade path later, and it just wasn't a blocker to main and launch.
Got it. All right, man. Well, I very much appreciate your time, and I know Rob does as well. Appreciate you coming on. I have plenty more questions about sovereign rollups as well, but I think we can save those for next time. Rob.
Yeah, sounds great.
Awesome. Thanks.
Plenty more
Thanks for having me on. That was great.
Awesome. Cheers.